There could be a lost continent beneath the United States, or let's put it this way, the geological remains of it. And that's actually even more exciting. After nearly 2 decades of data collection, a research team has created a new map of the US subsurface, and it suddenly reveals structures that no one had previously considered. The amazing thing is, this data could not only reveal how North America was formed in the first place, but might even help protect power grids from blackouts, and it shows massive resources like gold and other metals that are hidden under the ground of America, but also around the world. How we are able to peer hundreds of kilometers deep into the earth, what this lost continent is all about, and how this new map can help us find new resources, that's exactly what we are covering today. And with that, welcome to the German Science Guy. I'm Dr. Jakob Beautemps, and in Germany we say Los geht's. To understand the mystery of this lost continent, we first need to take a look beneath the surface of our planet. The Earth consists of different layers. In the middle, there's a core made of iron and nickel that's over 5000 degrees Celsius or 9000 degrees Fahrenheit hot. This immense heat rises and sets the other layer, the Earth mantle, into motion. Even though it's made of solid rock, the lower part of the mantle is a slow-moving liquid and deformable at temperatures of 2000 degrees Celsius or 3600 degrees Fahrenheit. This heat flow is the engine of our planet. It ensures that the tectonic plates of the lithosphere, that is the crust and the uppermost solid part of the mantle, do not remain rigidly fixed, they float on the softer mantle beneath them. This dynamic process faults mountains, causes volcanoes to erupt, and triggers earthquakes. But the most exciting thing is, at this depth, ancient material remains preserved for billions of years. It's like a geological archive where sunken tectonic plates and the scars of ancient continental collisions are preserved. Researchers had actually assumed that we had a pretty good understanding of the continents and their evolution, but geology is now showing us that we've only scratched the surface so far. After 20 years of intensive research, the United States Magnetotelluric Array Project has created a complete 3-dimensional map of the Earth's crust and upper mantle beneath the entire United States. The goal was to probe the continent to a depth of 500 kilometers or 300 miles in order to understand the invisible architecture of North America and the evolution of North American continent. And that's exactly what they achieved. They discovered hidden structures that are truly fascinating. I will go into detail in a moment, but first I will explain the technology behind it. How can you see into the Earth without light or drilling? The USMT Array Project is part of the Earth Scope program. The program combines various geophysical methods, namely seismology and magnetotellurics. The first method, seismology, uses vibrations and ground movements to see what the Earth looks like inside. To do this, researchers use either natural vibrations, such as those caused by earthquakes, or artificial waves, for example from controlled explosions. And yes, I know, that's a pretty brutal method, but it works. These seismic waves propagate through the Earth differently depending on how dense and elastic the Earth's crust is. Measuring these vibrations provides insights into the Earth's interior. And then there's the second method, which is, let's say, a bit more subtle, magnetotellurics, which was primarily used in the USMT Array Project. And in this project, it works entirely without artificial signals. It's a purely passive electromagnetic method. Instead of sending physical waves into the ground themselves, as in the case of seismology, the researchers harnessed nature, which are powerful lightning strikes and cosmic solar winds, to ultimately measure electromagnetic waves and electric currents. Lightning and solar winds are gigantic sources of electricity that generate extremely strong magnetic fields that are constantly changing. The magnetic fields penetrate deep into the ground and cause electrical currents to flow there. And depending on what the soil at the measurement point is made of, moist clay, metal or dry rock, the current flows with varying ease. So what we are actually measuring is conductivity. And the better the conductivity, the deeper and more undisturbed the currents flow. And by comparing the magnetic fields from the sources with the current flow from below, we get a kind of electrical X-ray image of the Earth's crust. The genius of this method lies in its range. We can use it to penetrate extremely deep, up to 500 kilometers or 300 miles. So seismic surveys by that reveal the structure of the Earth's layers, for example the density of materials, while magnetotelluric surveys detect the composition and the state of materials, such as whether they are molten or solid. And to measure exactly that across a wide area, a massive effort was required. The researchers distributed 1,800 stations across the entire United States to measure these signals. Measurements were taken at each location for several weeks, and in total they conducted measurements for 18 years. And the effort was worth it, because the result is a map that reveals the completely hidden structures of the North American continent. Dr. Moorkamp from the Institute of Applied Geoscience at the Technical University of Berlin in Germany explained to me what makes it so special.
The great thing here is that we have this broad overview of the entire continent, because, of course, there have been studies before, but they were always limited to, say, 100 by 100 kilometers or so. And now we can put it all into a very nice context.
And this map shows us these new connections for the first time, which depicts the Earth's total electric conductivity at depths ranging from 5 to 40 kilometers or 3 to 24 miles. Structures shown in white or red conduct electricity particularly well, while those in black conducted poorly or not at all. The original study mentioned many structures in detail that are too specific for this video, but Dr. Moorkamp helped us break down the results in 4 main areas. The Cascadia subduction zone is located in the northwest. This is because 2 tectonic plates, the North American and the Pacific plate, meet here. The oceanic crust subducts beneath the states of Oregon and Washington, and these conductive structures form along the coast. The high conductivity arises because fluid is drawn deep beneath the plates and resurfaces in active volcanic zones. Dr. Moorkamp emphasizes how important it is to be able to view the entire subduction zone as a whole. Only then can we better assess the region's earthquake risks. And then there's the second area in the west, the so-called Basin and Range Province. This is a vast area that is slowly being stretched apart. This stretching causes the Earth's crust there to be extremely conductive down to a depth of 35 kilometers or 20 miles, a big contrast to the rest of the region. Thanks to the comprehensive measurements, these are likely the clearest geophysical image of this region. And then there's the third region. It lies in the center of the US, the stable ancient inner core of the continent, what geologists call the craton. On the map it can be identified by the massive deep black areas. This means that the rock here conducts electricity extremely poorly because it is so old, cold and dry. And thanks to this data, we can now understand how this North American anchor that is over 2 billion years old is connected to the tectonic movements in the West. And then finally, there's one of the project's most significant discoveries. It's a Pittman resistor on the east coast. It's a massive fragment with low conductivity, and it extends 200 kilometers or 124 miles deep into the Earth. Researchers believe the resistor originated from the Earth's crust, which was formed by massive volcanic eruptions 200 million years ago. These eruptions are thought to be the reason why the American continent broke away from the rest of Pangaea, the supercontinent. This project is a milestone in basic geological research. For the first time, we are seeing the 3D architecture of the entire continent with this level of clarity and discovering structures that were previously invisible. But this map can actually do even more. This knowledge could prevent damage to power grids or even blackouts. We'll get to how that works in a moment, but please subscribe now so you don't miss any more videos and you support this channel for free. So this map isn't just exciting for science, it's also kind of a treasure map for critical minerals such as gold, copper or sulfides. The advantage here is that we get a deeper look than with conventional exploration. The project was able to identify so-called basement pathways, ancient highways in the crust along which mineral-rich fluids and metals rose to the surface millions of years ago.
At these locations, these minerals are concentrated in these fluids. They rise to the surface and form a concentrated area where you can say, there's now enough copper, gold or other metals here that it's worth building a mine or extracting the resources.
And then there's the even more striking and for me even more important application, disaster preparedness. The danger we are talking about comes from far away, more precisely 150 million kilometers or 90 million miles away from our sun. Violent eruptions on the sun's surface hurl clouds of particles into space. When these hit Earth, they trigger massive disturbances in the Earth magnetic field, a so-called geomagnetic storm. This in turn induces massive electric currents in the Earth's crust. The problem is that these induced currents seek the path of least resistance. And in areas where the Earth is not so conductive, such as the Pittman resistor, the currents often end up directly in our power lines and transformers, which can then lead to power outages and damage to infrastructure. And that's exactly where the new 3D map can help. The USMT Project has shown that certain types of rock can increase the risk to our power grid by a factor of 1000. Thanks to this data, researchers are now creating real-time hazard maps that warn utility companies in time to prevent transformers from being damaged and entire cities from being plunged into darkness.
And ultimately, this kind of conductivity structure of the Earth allows us, once we know how to say, well, if we have the next major solar storm, where are the critical points? Where is the greatest risk? And then you can start thinking, okay, what exactly do we need to do now to protect our infrastructure?
So these discoveries are truly spectacular, and the deeper I dived into the topic, the more fascinated I became. Partly because I've always found geology so exciting, but also because it's just great news. But you know how it is. When you dive down a rabbit hole like this, there's always one thing you have to do, and I do it in every video because my videos are structured the same way I write a scientific paper. In the paper, we outline the limitations, and in my videos, I call it the big hurdle. And here we are also going to take a look at the critical points of this new scientific news. So to start with it, the map from the USMT Project is definitely real and it is incredible. But we have to be careful about what we read into these images. By the way, if you like the approach of always looking critical at topics too, please subscribe. And if you want to support my work, you can also become a member of this channel, which directly helps me to pay my editors and to keep all of this running. But only if you want to. So let's get to the hurdle. The experiment did not uncover a complete preserved sunken continent. Instead, what we see are only fragments lying beneath the surface like a gigantic incomplete puzzle. And that's exactly where the risk of misinterpretation lies. While the map shows us precisely where the Earth conducts electricity and where it doesn't, the geological significance behind it is often the subject of ongoing research with many competing theories. It could be a continent, which is why I took the liberty of mentioning this in the title as well. But it's still being investigated further. And then there's another hurdle that has to do with the map's precision. The spatial resolution is about 70 kilometers or 43 miles, since the measuring stations were spaced that far apart. That means anything smaller than that distance remains blurry to us. And that's not quite precise enough, especially when searching for minerals. But that's more of a small hurdle to me, because this is after all a kind of a first step. Overall, this map is a great success and has even inspired similar large-scale projects, including in China, Australia and Brazil. And in fact, there isn't a map of Germany or Europe this detailed, at least not one that's comprehensive. That's because a project like this is a logistical feat. The US project alone required over 1,800 stations, each of which had to take measurements in the wilderness for weeks on the end. In Europe, with its many often small countries, this poses a huge challenge both geographically and above all politically. And added to this are human sources of interference. Magnetotellurics is very sensitive, and power lines, passing trains, pipelines or industrial facilities generate electrical noise that can completely mask the faint signals from deep underground. On a continent as densely populated as Europe, it is therefore very difficult to obtain a clean picture.
This threat to the power grid isn't yet very high on the agenda here. It's coming slowly, but a lot has happened in the last 2 years.
So the bottom line is that the new map shows one thing above all. The Earth has a damn good long-term memory. Continents and their history do not simply vanish without a trace. They leave behind scars, fragments and signatures deep within the Earth. And today, using methods such as seismology and magnetotellurics, we can reveal these traces piece by piece. The lost continent beneath the United States is therefore probably not a sunken Atlantis, but rather a geological archive. At the same time, the project also shows that such maps are more than just basic research. They can help us better understand natural resources, verify geological models, and in the best case scenario, even better assess risk to infrastructure and power grids. But one thing is also clear. A map like this is not a direct photograph of the Earth's interior. It's a model, a very complex and extremely useful model, but still just a model that must be interpreted. And that is precisely why this topic will likely keep us busy for quite some time. And if there's a news on this topic, I of course will make an update video about it. And if you're also fascinated by the world, please take a look at this video. I was at the biggest solar park in the world, or let's say one of the biggest. It's the biggest one single site solar park. I think it was incredible, and if you like to watch it, please do so. And I say Auf Wiedersehen, which means goodbye in German. Thank you for watching. Vielen Dank, dass ihr zugeschaut habt. Your Jacob.